Hi, in this video we are going to talk about problems with array data structure so that we understand the problems and we feel the need of linked list data structure. Array is a sequential data structure. It stores elements at contiguous locations. Linked list, on the other hand, drops the requirement that elements have to be at contiguous locations. Linked list is also sequential data structure, linear data structure. And these two data structures are the biggest competitors of each other. At many places, you can either use an array or a linked list. For example, implementation of other data structures like stack, queue, dequeue. These data structures can be implemented either with arrays or with linked lists. So before we begin linked list, let's see what all problems are there in arrays. We generally see these types of arrays in C++. This is an array of fixed size. I've created an array of size 100 here. It can be any other fixed value like 200, 1000 or any other number. This is a variable sized array where user can specify I want an array of size n, where n can be any number, any user input also. This is a dynamically allocated array. These two arrays, if they are local arrays, they are allocated on the stack frame of function, right? This array is dynamically allocated on heap. So this is a dynamically allocated array. These arrays, they go out of the scope when your function is over. This array, allocated array, stays there, right? It does not go out of the scope. The last array in C++ is vector, which is a dynamically sized arrays. They grow when you add more and more elements. They grow automatically. You do not have to specify the size. You can specify the size if you want compiler to optimize according to the requirements, but you do not have to. You can put as many elements as you want and it will grow automatically. Let's talk about Java. Java also has fixed size arrays, variable sized arrays. These arrays in Java are always allocated on heap. They are always dynamically allocated. They are always created this way. Even this array is allocated on heap. The next array in Java is array list, which is similar to vectors. They grow automatically. When you push more elements than the current capability, they'll grow automatically. You can also specify the size here, like vectors. If you want to optimize the space, in advance these many elements are going to be there, you can use them. Array lists and vectors, they both store elements at contiguous locations. They ensure that they store elements at contiguous locations. And it's up to the compilers to decide their implementations. Whatever implementation they decide, they have to make sure that elements are contiguous and arrays grow and all provide all the other functionalities of this collection vector, right? So vector and array list, they are dynamic sized arrays. They grow automatically. So we have all these arrays, they provide different functionalities. What are the problems with these arrays? Why do we need another sequential data structure which is going to store items in sequential manner? Let us now talk about problems with arrays. The first problem with arrays is we need to pre-allocate the space. And the space allocated is fixed, where either it is 100 or it is some n, right? So once you've decided that there are going to be n elements in the array, it's going to be n only. You cannot insert any more elements. This problem is solved by dynamic sized arrays. Dynamic sized arrays which adjust their size whenever they become full. And examples of dynamic sized arrays we discussed, right? Vector in C++, array list in Java, list in Python. And what do? They double the size. Whenever they reach their limit, they double the size in their typical implementation and they copy the previous elements to the new allocated double space. But the problem with this approach is, with this vector, array list or list approach in Python is, you have an operation which is big O of n. Sometimes your insertion, even it is done at the end, it can become big O of n. So while your array has space, it's big O of 1, and when it becomes full, it becomes big O of n, even with dynamic sized arrays. What if you want working in a real-time environment where you do not want any particular operation to be costly. In that case, you can't use such data structures like vector, array list, or list. However, on average, they take big O of 1 time. There's only one operation which is big O of n, then there are many operations which are big O of 1. And if we do average time complexity computation using amortized analysis, then we can see that it's on average big O of 1 operation. But the worst case complexity is still theta n big. And if you do not want that worst case, then these data structures are not suitable. The other disadvantage of array is insertion in the middle is costly. So I think we all know it, right? Because they have to be contiguous. So if you have elements like 10, 20, 30, 40, and say you have space for more elements in the array, and I want to insert say 25 here, what will happen? I'll have to move these two elements one position ahead. So I'll have to run a loop. And then I'll have to modify this array to this 10, 20, 25, 30, 40. This element has to be moved here. This element has to be moved here. And then you can insert 25 because they have to be contiguous, right? So this is a costly operation. Suppose there were thousands of elements in the array and you wanted to insert something at the second position. So you will have to move 998 elements one position ahead, right? So you need to run a loop for all the elements, almost all the elements if you're inserting at the beginning. Now, same reason for deletion. Suppose you have this array and you want to delete 20 from it. What will happen if you delete 20? You will have to move these elements one position before, right? So your array will become something like this. If you delete 20, it will become 10, 30, and 40. Suppose you had thousands of elements and you wanted to delete the second element or first element, then you will have to move almost all the elements one position before, right? If you are moving the first element, removing the first element, then you will have to move 999 elements one position before, which is a costly operation. So insertion in the middle, deletion from the middle, they are both costly operations. Third thing is implementation of data structures like Q and DQ. So if you're talking about stack implementation, if you have not studied stack and queue, you will get this point later, but let me just explain for those people who have studied. So if you're talking about stack, insertions and deletions, they both happen at the same end, and you can use the last end of the array and implement stack. But if you're talking about queue and DQ, efficient implementation is not easy with arrays because insertion happens at one end and deletion happens from the other end, right? In DQ, insertion and deletion both happen at both ends. It's possible to do all the operations in big O of 1 time, even with arrays, but the implementation is complex. And with linked list, the implementation is super easy. We can simply implement Q and DQ using linked list. Let us talk about first problem, which is difficult to implement using arrays, and it's very easy to implement using linked list. In particular, a variation of linked list called circular linked list. We'll talk about this variation in the upcoming video. Here, the purpose is only to explain the problems with array implementations. Say we have a processor queue of processes and we are using round robin scheduling, and every process gets a quantum of 5 units. So you begin with P0. P0 needs 10 units, 10 CPU cycles or 10 time of CPU, right? So what do? You assign 5 to it in this quantum when it is assigned, and you want this to be moved to the end of the queue, right? You want it to go away from here, from the front of the queue, and move to the end of this queue. So P3, P4 and P5 are here, and then comes P0, right? So it is assigned 5 units and goes to the end. So you have 5, 3, 15, 10, 8. And now how many units it needs? It needs 5 more units, right? So that's the setup now. After 5 units are allocated to this, a token is allocated to this. Now turn of P1 comes. So P1 needs 5 units only. So when P1 needs 5 units and you give it 5 units, it's over. So you want to remove P1 from this, right? From this queue of waiting processes. So you have P2 now. Sorry, you have P2 now, P3, P4, P5 and P0. So you have only these processes in the queue left now, right? So you removed P1 because P1 is done. Now you allocate processor to process P2, it gets 5 units, but it needs only 3 units. So P2 finishes and P2 also goes out of the waiting queue, ready queue of the process. So we have 15 gone, 10 gone, 15 now, 10, 8 and 5. So this is out now, P3, P4, P5 and P0. This is your new ready queue of the processes. So what is happening here? You need to select an item and remove it from the queue, right? Ready queue of the processes. And sometimes you need to remove it from its current position and insert at the end. If you go and implement this using array, it's going to be really difficult. If you use simple array implementation, what will happen? You will take out this item, right? Take out this item and remove it from here and insert at the end, right? That's what you did here, right? Here you will totally remove this item, then you will remove the next item as well. So this is the problem with arrays. It becomes really difficult to implement such problems with normal arrays. Let us consider one more problem which is not very easy to implement using arrays. So the problem says we are given a sequence of items. Whenever we see an item X in this sequence, we need to replace it with 5 instances of another item Y. Say we have the sequence, so we do not change anything else except X. Whenever we see X, we replace it with 5 instances of Y. We do not know priorly how many instances of X are there. So when we see Q, we process it, VR, we process it. When we see X, we replace it with 5 instances of Y. When we see P, we process it. When we see Y, we process it. So if you implement it using arrays, what will happen? You will have to have one more array. So one option is you do not know how many axes are there, so you count how many axes are there. You allocate that big array. So if this count of axes is say n, then you need to have an array of size n into 4 extra, right? Because one x is being replaced by 5 y's. And then you will put these items into that new array. So you will put D as it is into the new array, E as it is into the new array, A as it is into the new array. And then you will put this x, in place of this x, you will put 5 y's in this new array. So this is one implementation. The problem with this implementation is you are doing 2 iterations. First you are counting how many x's are there. Then you are traversing next time to replace every x with 5y. You can avoid one count using dynamically sized array, using dynamic sized arrays like vector or list, right? What you can do, you can just create an empty vector in C++ or empty array list in Java, and you can, whenever you see x, you put 5 y's in this. But still, you need extra space. You need extra space for allocation of output, right? With linked list, you can do this in the same sequence. So if you have to modify the same sequence, again, it's really difficult. It's really difficult because in the array implementation, what you were doing, you were allocating a new array list or vector. But if you have to modify the same sequence, how will you do it using array? You will have to allocate a new array. With linked list, it's super easy. We'll see when we do some questions on linked list. Here is third problem, which is difficult to do with arrays, and we can do it better using linked list. This problem actually I've taken from the merge sort. What happens in merge sort? If you are sorting an array using merge sort, you will need auxiliary space for merging, right? But if you are sorting a linked list using merge sort, then you would not need auxiliary space, because in linked list you can do insertions and deletions at random positions, but in arrays you can't. So you will have to copy the original arrays and then you will have to do the merge. So here is an example similar to that merge process. So see, we are given a problem where we have multiple sequences and we have queries on these sequences, where every query says that we need to merge the sequence number with the sequence number. So when I process this query merge 0 1, what I mean is these two sequences should be merged. and my new sequences after this query should become so 0 and 1 are merged, so they become 1, 5. Then we have the next sequence. Then we have the next sequence. Now we say merge 1 and 2. So these two sequences should be merged. And our modified sequence after this should be so if you store these sequences as an array, for merging you will always need an auxiliary array, right? And merging would be a costly operation in terms of space. But if you store these sequences using linked list, then you can do these merge operations in the same time, but you would not need extra space. So extra space means extra overhead also, because you will have to copy these sequences to the extra allocated space. So that will be like time wise also more. Constants would be higher in time as well. But if you're using linked list, you do not need to copy, you don't need to allocate a new space and then copy these sequences to those every time you're doing a merge, right? But in case of array implementation, for every merge, you will have to allocate extra spaces. So we have talked about multiple problems with array data structure. One more problem with array could be in system programming. Suppose you are making some system level program, you have limited memory environment and you want to make sure that you have enough space to allocate for larger data whenever you need. What will happen in case of arrays? If your memory is fragmented, if it is fragmented, if different chunks of memories are allocated, then you would not be able to allocate a large array because you would never get contiguous space. But if you're using linked list, then you can link these available spaces and you can do better. So this is another advantage of linked list. Let us introduce the linked list now to get an idea how linked list does better compared to arrays for these problems and how does it handle this fragmentation problem better. If you have studied the linked list already slightly, then you must have got the idea. But let us introduce a linked list now.